High neutral currents in transformers can be significantly impacted by harmonic loads. When a transformer feeds loads that generate harmonics, such as electronic devices or variable frequency drives, the neutral conductor can experience current levels exceeding those in the phase conductors. Under balanced conditions, with equal current flowing through each phase conductor, ideally the neutral current should be minimal or close to zero in a three-phase, full-wire system. However, harmonic currents, specifically triplet harmonics, which are odd multiples of the fundamental frequencies such as the third, ninth, and 15th harmonics, are additive in the neutral conductor. These triplet harmonics are in phase with each other and do not cancel out like the fundamental frequency currents. Consequently, they accumulate in the neutral, potentially leading to a neutral current that is substantially higher than the individual phase currents. Firstly, unbalanced phase conductors exacerbate this issue. If the phase currents are not balanced, the neutral conductor must carry the difference in current between the phases to maintain system equilibrium. This imbalance at the fundamental frequency adds to the harmonic currents already present in the neutral, further increasing the overall neutral current. A significant imbalance in phase currents, combined with substantial harmonic distortion, can create a situation where the neutral current far exceeds the rated capacity of the neutral conductor and the transformer's neutral winding. Secondly, the high neutral currents on the load side of the transformer can have cascading effects in the line side, that is, the upstream components of the electrical distribution system. The transformer's neutral terminal is typically bonded to the secondary neutral, allowing neutral current to flow through the transformer's windings and back to the source through the line-side neutral conductor. This can lead to several problems. One problem is overheating. The excessive neutral current can cause overheating of the transformer's neutral winding, the line-side neutral conductors, and any connected panels and switchgear. Overheating can degrade the insulation of conductors and windings, leading to premature failure of the transformer and other electrical components. This, in turn, can result in costly repairs, downtime, and potential safety hazards. 2. Voltage distortion is also another problem. High neutral currents can contribute to voltage distortion on the line side of the transformer. The harmonic currents flowing through the system impedance create voltage drops at harmonic frequencies. These voltage distortions can affect the performance and reliability of other equipment connected to the same electrical system, such as motors, electronic devices, and sensitive control systems. Voltage distortion can cause equipment malfunctions, reduced efficiency, and increased wear and tear. 3. The increased stress on upstream equipment also comes into play. Elevated harmonic currents and voltage distortion on the line side of the transformer can place additional stress on upstream conductors, panels, switchgear, and other distribution equipment. This stress can accelerate the aging of these components and increase the likelihood of failures. It is crucial to consider the potential for high neutral currents when designing and selecting electrical systems, particularly those serving harmonic producing loads. To mitigate the effects of high neutral currents, several strategies can be employed. One strategy is to reduce harmonic generation at the source. This can be achieved by using harmonic filters, line reactors, or other power quality equipment to minimize the harmonic content produced by nonlinear loads. Active harmonic filters can inject compensating currents into the system to cancel out harmonic currents, while passive filters use inductors and capacitors to block or shunt harmonic currents. 2. Balancing phase loads is another strategy. Ensuring that the phase loads are as balanced as possible minimizes the fundamental frequency current flowing in the neutral conductor. This can be accomplished by carefully distributing loads across the three phases and avoiding excessive single-phase loads. 3. The use of oversized neutral conductors can mitigate the effects of high neutral currents. Increasing the size of the neutral conductor provides a lower impedance path for harmonic currents, reducing voltage drop and minimizing overheating. The neutral conductor should be sized to handle the anticipated harmonic current load, often requiring a conductor larger than that required for the phase conductors. 4. Using K-rated transformers can also help. K-rated transformers are designed to withstand the heating effects of harmonic currents. These transformers have a high capacity to dissipate heat generated by harmonic currents, reducing the risk of overheating and extending the transformer's lifespan. The K rating indicates the transformer's ability to handle nonlinear loads without exceeding its temperature limits. 5. The application of dedicated neutral conductors is another strategy to use. In critical applications, it may be necessary to provide a dedicated neutral conductor for each phase. This isolates the neutral currents from different phases, preventing them from adding together and reducing the overall neutral current. Dedicated neutral conductors are particularly effective in systems with high harmonic distortion or unbalanced loads. 6. Monitoring and analysis is also another solution. Regularly monitoring and analyzing the electrical system for harmonic distortion and neutral current levels can help identify potential problems early on. This allows for proactive measures to be taken to mitigate the effects of high neutral currents and prevent equipment failures. Power quality analyzers can be used to measure harmonic voltage and current levels, providing valuable data for troubleshooting and optimization. In addition to these mitigation strategies, it is essential to comply with relevant electrical codes and standards such as the National Electrical Code, or NEC, which provides guidelines for conductor sizing, overcurrent protection, and grounding to ensure safe and reliable operation of electrical systems with harmonic loads. For example, NEC Section 220.61 addresses the sizing of neutral conductors for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and electric dryers. It specifies that the neutral load can be calculated as 70% of the unbalanced load. This provision recognizes that in typical residential applications, the neutral current will be less than the maximum unbalanced load due to the statistical diversity of appliance usage. For feeders supplying electric ranges, ovens, and cooking units and dwelling units, NEC Section 220.55 provides specific demand factors to account for the likelihood that not all appliances will be operating at their maximum load simultaneously. These demand factors reduce the calculated load for the feeder, taking into account the diversity of appliance usage. NEC Section 220.20 covers the calculation of feeder loads for banks or groups of similar loads. It allows for the application of demand factors to account for the probability that not all loads will be operating at their maximum demand simultaneously. This provision is particularly useful for large installations with multiple identical loads, such as office buildings or industrial facilities. The NEC also addresses the sizing of neutral conductors for electric vehicle charging equipment. As electric vehicles become more prevalent, it is important to ensure that the electrical system can safely and reliably support the charging load. The NEC provides guidance on calculating the neutral load for electric vehicle charging equipment, taking into account the charging current and the number of charging outlets. Furthermore, in commercial and industrial settings with significant nonlinear loads, the NEC requires that the neutral conductor be sized to carry the maximum unbalanced load, including harmonic currents. This provision ensures that the neutral conductor is adequately sized to handle the increased current flow due to harmonic distortion. The effects of harmonics on transformers and neutral conductors are complex and can have significant consequences if not properly addressed. By understanding the sources and characteristics of harmonic currents, implementing appropriate mitigation strategies, and adhering to relevant electrical codes and standards, it is possible to ensure the safe and reliable operation of electrical systems with harmonic loads. In summary, high harmonic loads can significantly increase neutral current in transformers. Unbalanced phase conductors exacerbate this issue, leading to even higher neutral currents. This can overheat transformer windings and affect upstream equipment, causing voltage distortion and potential equipment failures. To mitigate these effects, it is essential to reduce harmonic generation, balance phase loads, use oversized neutral conductors, employ K-rated transformers, apply dedicated neutral conductors, and regularly monitor and analyze the electrical system for harmonic distortion. Compliance with relevant electrical codes and standards is also crucial for ensuring safe and reliable operation of electrical systems with harmonic loads.